Welcome to Zoning Hydronic Heating Systems, another of Weil McLean's hydronic education and training video-based programs. I hope you've had the opportunity to experience some of our other heat video-based training courses, but if not, here's how the program works. This course will explore zoning hydronic heating systems, the basics of hydronic systems, why we might want to zone, the theory of controlling water flow, how to zone with circulators, how to zone with electric zone valves, zoning with non-electric zone valves, and finally, steam zone valves. Throughout this course, at regular intervals, we will ask you to stop the videotape so you can review each section of the program using the workbook. Also remember that you can rewind and review the video segments at any time. The first section will cover the fundamentals of hydronic heating systems. What are the components of a basic system relative to zoning and system piping? Throughout this course, we will be looking at actual installations of hydronic heating systems. You'll see zone systems using circulators, electric and non-electric zone valves, and steam zone valves. We will also be pointing out various system components found in these systems. Basically, a hydronic heating system consists of a boiler and circulator, water piping, and some type of room terminal, either baseboard, radiator, or radiant panel. Hot water is generated in the boiler, moves through the piping to the room terminals where the water gives up its heat and then returns to the boiler. One of the major benefits of hydronic heating is that water has the capacity of carrying and retaining a lot of heat. Because of this excellent capacity to retain heat, even when the thermostat is satisfied, the heated water remains in the room terminal and it continues to provide comfort to the room. There are no abrupt temperature changes with a hot water heating system. The temperature difference between a room's ceiling and floor is usually only 1 to 2 degrees with hydronic heating. Up to a 10-degree difference might be experienced with a warm air system. Another key advantage of hot water heat is the ability to regulate different temperatures in different rooms. Establishing independent heating zones in a home is relatively simple with hot water systems. By doing this, main living areas can be kept at a higher room temperature than bedrooms or rooms that are seldom used. Besides the economics of being able to control individual room temperatures, zoning with hot water heat provides maximum comfort flexibility for everyone in the home. But more on zoning later. For our discussion, we want you to be aware of how the following components work: limit controls, circulators, and flow control valves. Limit controls are thermally activated switches that are designed to react to changes in water temperature. Most limit controls have an adjustable high limit setting with a 10-degree fixed differential. The high limit setting is used as a temperature protection device for the boiler. If the boiler water should reach the high setting, the limit switch would cause the burner or burners to shut off and stop producing heat. The circulator continues to operate, removing heat from the boiler and distributing it to the terminals until the water temperature is lowered the 10 degrees of the fixed differential. As long as the thermostat is calling for heat, the boiler refires after the water temperature is lowered to the 10 degrees of the fixed differential. Limit controls can also be adjusted for seasonal operations. For example, standby losses can be reduced by setting the control to 170 degrees Fahrenheit in the spring and fall, and 180 to 210 degrees Fahrenheit in the winter months. Limit controls act like light switches. They open on a water temperature rise and close when water temperature falls. Another common hydronic heating component is the circulator. The most common circulators found on residential boilers are single-stage centrifugal pumps. The circulator's job is to force water throughout the hot water system. The The circulator contains an impeller with a number of vanes which rotate at a high speed to move water through the system. There are a couple of ways to isolate a circulator so that if replacement is necessary, you don't have to drain the system. One way is to install ball valves on either side of the circulator, as you see here. Isolation flanges can also be installed on either side of the circulator and only require the use of a screwdriver. On multiple zone systems using circulators, a flow control valve prevents gravity circulation of system water when the circulator is not in operation. The valve allows system water to flow in only one direction when the circulator is operating. We'll cover the flow control valve in more detail in Section D. Next, we want to discuss different methods for piping hydronic heating systems. Series loop piping systems are usually found in residences and small buildings. This piping system uses one continuous loop or circuit from the boiler supply pipe through the heating terminals and back to the boiler return pipe. The heating terminals are usually baseboard units with everything connected in one continuous loop. Series loop systems can also be divided into two or more circuits. A circuit is one complete loop from the boiler supply piping through the terminals and back to the boiler return piping. Water flow is typically divided into approximate equal flows throughout each of the loops in the system. A one-pipe system uses one continuous pipe, called a main, from the supply of the boiler to the boiler return. The terminals are connected to the main by pipes called risers, one for the supply and one for the return. These risers must be connected to the main using special T's called one-pipe fittings. You might also hear them called monoflow or Venturi fittings. In a two-pipe system, one main pipe carries the heated water from the boiler supply tapping through the system, and another main pipe carries the cooler return water back to the boiler. This system uses a supply main and a separate return main. There are two types of two-pipe systems: reverse return and direct return. In a reverse return two-pipe system, the terminal that is connected first to the supply main is the last terminal connected to the return main. Because of this, the water in a reverse return two-pipe system travels approximately the same distance through each terminal and back to the boiler. This provides for a balanced flow of water through each terminal, allowing for individual control of heat from each terminal without affecting water flow. The reverse return two-pipe system may be found in some residential heating systems and is usually the standard piping system for commercial jobs. In a direct return two-pipe system, the first terminal connected to the supply main is also the first terminal connected to the return main. In this system, the distance the water travels through the first terminal is much shorter than the distance the water travels from the last terminal, therefore creating a more difficult system to balance. Direct return piping systems were commonly used with old-style gravity hot water heating systems. In forced circulation systems, controlling and balancing is more difficult. Radiant panel systems circulate hot water through a series of pipes located in either the floor, ceiling, or walls. In this system, the floor, ceiling, or wall acts as the terminal. Typically, radiant systems are reverse return two-pipe systems to prevent the water from short-circuiting through the shortest distance in the system. There is a resurgence in the use of radiant systems due to the less expensive plastic piping. Remember that oxygen-impervious plastic pipe needs to be used in these types of systems to help protect the boiler from oxygen corrosion. In this section, we have discussed the basics of hydronic systems, how hot water is generated, a few of the major components of a hydronic heating system, and piping systems. In the next section, we will discuss the principles of zoning systems. Turn the videotape off now and complete Section A in your workbook. should now have a basic understanding of hydronic heating systems, how they operate, and how they're piped. Next, let's discuss the zoning of hydronic systems, why we would want a zone, and some basics behind zoning. You might wonder, what is zoning? What does zoning mean? A zone system is nothing more than a room or group of rooms in a residence or commercial building which are served by separate piping circuits and a control devised to maintain temperature. Each of these circuits, or zones, are separate from one another as they provide heat to distinct parts of the house, but they share the boiler as the single heating source. The main purpose of zoning is to independently control the temperature of a given area. In a zone system, heat is delivered to the individual zones only when it is called for. By being able to maintain different temperatures throughout a house, the heating system offers a great deal of flexibility. In recent years, residential construction trends indicate more larger, multi-level homes with large glass areas and fireplaces. Because of these large window and door areas, zoning the heating system can compensate for these trends in building construction with different heating requirements. By reducing temperatures in room areas such as bedrooms, zoning provides for a more efficient heating system operation, reducing fuel consumption. If the decision is made to add zoning to a new hydronic heating system installation, the costs can be greater than a series loop or multiple circuit piping arrangement. This cost is due to the additional equipment necessary to create the individual zones. However, once the system is in operation, savings will be generated. Heat to each zone will be increased, reduced, or even eliminated depending on the family's needs. Also, certain types of buildings benefit from zone systems. The larger the structure, the more crucial zoning becomes. Buildings that contain differing occupancies, such as combined medical and retail buildings, can benefit from zoning as the time of operation of the businesses may differ. Commercial buildings such as hotels, motels, hospitals, and nursing homes that need independently controlled rooms benefit with zone systems. In addition, these buildings require instant heat upon demand. Single circuit systems tend to overheat upper levels on multi-level homes and underheat lower levels. With zoned heating, the temperatures can be balanced between levels. Also, if a hydronic system contains two or more different types of radiation, such as baseboard or radiant floor panel, zoning can balance out these temperature differences. There are three basic methods used to zone hydronic systems. Circulators can be installed on each zone, and when there is a call for heat, the zone circulator moves water through the zone. A zone system can also incorporate electric zone valves. These valves are electrically controlled globe valves that open and close based upon a call for heat from the thermostat. The third method uses non-electric zone valves, which can be installed at each piece of baseboard or radiator. Each one of these methods of zoning will be discussed in more detail in later sections. Before examining these methods, we want to explain two concepts in the next section: flow rate and pump head. These two concepts must be understood before you undertake the sizing of a zoned hydronic system. But before we do, let's turn the videotape off now. Take a few minutes to review the section and complete Section B in your workbook. Before we discuss how to actually zone a system, there are a couple of system sizing concepts that we need to cover. The first is flow rate, or GPM. The second is pump head. Earlier, it was stated that one of the major benefits of heating with hot water is that water has the capacity of carrying a lot of heat. Since most piping systems today are forced circulation systems and no longer gravity-fed, a circulator is used to move the hot water from the boiler out to the system. The flow rate is defined as how fast the circulator can move the heated water. The goal in zoning a system is to make sure that the right amount of heated water goes where it's supposed to go, when it's supposed to go. Whether designing a new hydronic heating system or working on a replacement job, the system should be designed with a specific temperature drop. A 20-degree Fahrenheit temperature drop is the industry standard. What this means is that the system is designed for a 20-degree drop or decrease in the temperature of the water from when it leaves the boiler to when it returns. In other words, if the water leaving the boiler is 200 degrees Fahrenheit, it would return at 180 degrees Fahrenheit, or a 20-degree temperature drop. The flow rate of a hydronic system is calculated in gallons of water per minute, or GPM. In other words, how many gallons of water can move or flow through the system in 1 minute? To start with, a gallon of water weighs approximately 8.33 pounds. Since a boiler is rated in BTUHs, or BTUs per hour, we use 60 minutes as a factor. By multiplying the 8.33 pounds times 60 minutes times the 20-degree system temperature drop, you arrive at 9,996, or rounded to 10,000 BTUH. This figure, 10,000 BTUH, is the industry standard that is applied to determine the gallons per minute requirements for residential hydronic heating systems. If a home's total heat loss has been calculated and determined to be a heating load of 75,000 BTUH, divide by 10,000. This number, or 7.5 GPM, is the required flow rate for your boiler. An 80,000 BTUH boiler has an 8 GPM flow rate, and a 135,000 BTUH boiler would require a 13.5 GPM circulator. Because different pipe sizes limit the ability of the system to deliver an adequate supply of heat, the correct sized pipe as compared to BTU capacity and flow rate must also be determined. Standard fin tube baseboard radiation is typically 3/4 inches. So let's assume that we're piping a house with all 3/4 inch pipe. By looking at the flow rate pipe size chart, a 3/4 inch copper pipe has a maximum gallons per minute flow rate of 3.5 GPM. This means that this 3/4 inch copper pipe is limited to a flow rate of 3.5 GPM. By multiplying 3.5 GPM by the standard 10,000 BTUH per gallon of water, a 3/4 inch copper pipe can carry approximately 35,000 BTUH. Taking flow rate and pipe size capacity into consideration, let's work through an example. A single-family residence with a total heat loss of 85,000 BTUH. What you need to figure out are the total gallons per minute required to supply the entire house. Remember the formula just covered. 85,000 divided by 10,000 equals 8.5 gallons per minute required flow rate. This means the heating system must be able to deliver 8.5 gallons of water per minute to supply the heat loss of 85,000 BTUH. Another way to determine gallons per minute for the house is to calculate the gallons per minute requirement for each zone. For this example, let's say that there are 5 zones in this house. 1.0 GPM for Zone 1, 1.3 GPM for Zone 2, 1.5 GPM for Zone 3, 2.2 GPM for Zone 4, and 2.5 GPM for Zone 5. As you see, The total number of gallons per minute required for the house, 8.5, can either be determined by adding up the individual zone GPM figures or by using the total heat loss figures for the house. What this all tells us is how many gallons per minute we can expect to move through a given size pipe. By multiplying this flow rate by 10,000, we can tell how much heat the water flowing in a pipe can carry, based on a 20-degree Fahrenheit temperature drop. Finally, we need to calculate how much baseboard a circuit or zone should have. To determine the length of baseboard needed, divide the heat loss by the net IBR water rating with capacities in BTUH per lineal foot of baseboard. You'll find these figures in the manufacturer's literature. As an example, if installing Weil-McLain Thermatrim baseboard, use this table to determine the appropriate number. The net IBR water rating in BTUH per foot of Thermatrim baseboard based on an average water temperature of 200 degrees Fahrenheit